All right, welcome to the second lecture on stability of synchronization. So what I've done here is I've given you two more of these systems that we're looking at, that we looked at the last time. So the last time we had a network of two nodes, right? So remember we had two nodes, we coupled them together, we got an ODE out of it, which we analyzed. So now I have here two more examples, now both with three nodes. So for the rest, the setup is all the same, right? So just to recap, I have that original ODE. So x dot is a times x, where a is a positive constant. So this is just happening on R again. And what I do is I start adding interaction terms, which look like this, which depend on a constant alpha, which is typically zero or positive. And if there is a connection between, say, nodes 1 and node 2, because, right, if there's a connection between them, then I add a term alpha x2 minus x1 to the dynamics of x1. And similarly, of course, to the dynamics of x2, I add a term alpha x1 minus x2 because the connections in this, at least at this part of the course, connections are both ways. They're undirected. If A feels B, then B also feels A in the exact but opposite way. So then we have a system like this. So here I've written it for the network on top, but you can of course also do it for other networks. So here I've done it for the all-to-all coupled network on three cells, right? So you just get a couple of additional terms, two additional terms, which directly correspond, of course, to this connection over here. Now, what I also explained, and this holds in more generality, is that I can write these systems, these linear systems as x dot. So here the capital X is all three separate variables stacked together, stacked on top of each other. So this is now a vector in R3. So big X dot is a matrix times X. So like I said, these are still linear systems. And so this A is, of course, the same A as we have in the equations. The alpha, the coupling strength is the same. The identity is just the 3 by 3, in this case, 3 by 3 identity matrix. And this L is, of course, the important bit. This L captures the interaction structure. This L somehow gives to us the structure of the network. So in this example, the top example, we have this L, which you can check by just writing out this linear equation in this form. You will see that this is the value of L, that this matrix. And here in the all-to-all coupled example, L is slightly different, of course, because the network is different. So how do you go about analyzing these systems? So the first thing we note, and this is a feature of all these kinds of coupled systems, and later we'll see them in a bit more generality, but we'll always have this fact, is that I can always define a space where all the states of all the nodes are exactly the same. So this is going to be one linear vector space, one linear subspace, and the dimension will just be one, or in a more general setting, the dimension will be the dimension of the phase space of a single node. And on there, so first of all, of course, this space is flow invariant, meaning that if I start my initial condition on this manifold, this linear space, it stays on there, right? Which you can check by just plugging in the same value for x1, x2, and x3, and noting that the equations of motions for all three cells are the same. And if you do that, in fact, you find that the dynamics on this flow invariant space is just given by u dot is a times u, where u is any of these variables, right? Because they're the same. And this is, of course, just the dynamics of the isolated node. So we find the dynamics of the isolated node in there on this flow invariant space. And there's nothing we can do about that by changing alpha. Whatever a value of alpha is, this fact will always remain true. And it's of course true for the system on top, but also for the system below. In fact, this is a general fact of these systems, no matter how many nodes, no matter what your network looks like. But then, of course, noting that we cannot change those dynamics, we can change if there is synchronization. In other words, if I start off of this manifold, maybe close by or maybe far away, but not on it, um, will the dynamics of the nodes start going towards that space? In other words, will they start behaving the same? Will we have synchronization, or will they just fly away? In other words, if I start, maybe I have a bunch of nodes and they act slightly the same, maybe they will just start doing completely different things. And that's the question that we set out to answer. Now, writing the equations like this in matrix form, we see that the only real thing that we're changing between the two systems on top and below is this excuse me, is this matrix L. So something about the matrix L will, of course, give us the difference between the two. So what is the first thing you, of course, try to do when you see a matrix? You start looking for eigenvalues and maybe corresponding eigenvectors. That's not always possible, as in that's not always possible for real matrices with real eigenvalues, and you cannot always find eigenvectors that span the entire space. But in this case, we have symmetric matrices, right? Both these matrices are symmetric. And that means we can actually find an orthogonal system of eigenvectors corresponding to real eigenvalues. So in this case, we can just find a coordinate system in which L is just a diagonal matrix of real entries. So when you look at this matrix, let's say the top one, you find that one eigenvalue is always given by 0. This corresponds, in fact, to the eigenvalue which has the same entry for each node, 1, 1, 1. And of course, what we will see is that this corresponds exactly to the fact of life that we have this flow invariant space on which the dynamics are just trivial, are just that of a single node. So this eigenvalue we always have. Turns out that for this particular Laplacian, the other eigenvalues are going to be given by 1 and 3. So you can do a quick sanity check. If you add 0, 1, and 3, you get 4, which should be the trace of this matrix, which indeed is correct. And because we can diagonalize this, we can diagonalize this matrix here as well, because the identity always plays nice with diagonalizations, with conjugacies. So if we go to those new coordinates, we find that in some sense, all of the dynamics has been decoupled again. So we get u dot v dot w dot. These are our new coordinates, and they will be given in quite an elementary form. U will only depend on u, v will only depend on v, and w will only depend on w. And these are just coordinates that diagonalize our Laplacian L over here. So we just get u dot is a times u, which of course corresponds to this phenomenon. For v, we get a minus 1 times alpha, corresponding to that eigenvalue 1. So just times alpha v. And here we get a minus 3 alpha times w. And this 1 over here and this 3 over here, those are just the eigenvalues 1 and 3 that we have here. So correspondingly, this a is just going to be a minus 0 times alpha. And now we're in business because now we can actually see, we can precisely see when we will have synchronization. So um, when the synchrony space over here is stable, so in these new coordinates, this synchrony space will actually correspond to V is zero and W is zero. So when is that space stable? Precisely when, or say asymptotically stable, precisely when the other coordinates, the V and the W, they go to zero. So for that to hold, we simply need that A minus alpha is smaller than zero. And we also want, of course, that A minus 3 alpha is smaller than zero. Now recall that alpha was positive and A was positive as well. So if I have this condition over here, if I know that A minus alpha is already smaller than zero, well, then certainly A minus 3 alpha will also be smaller than zero, right? Because their difference is minus 2 alpha. If this one over here is negative, then here I'm subtracting even more alpha, so that one will be negative 2. So that second property is superfluous, it's redundant. So the property that we need for synchronization is in fact that A minus alpha is smaller than 0. So in other words, again, alpha has to be bigger than A. So it's slightly different because in that first case, remember our first network, we had that alpha had to be bigger than A over 2. So that was a weaker condition. Now alpha, in fact, um, has to be bigger than A. So let me put that alpha has to be bigger than A. So if we couple them strong enoughly, precisely this strong, then we will see synchronization. Now, if you look at this second example over here, you find slightly different coordinates. You find a slightly different system. So you can make this guy diagonal as well, but now the eigenvalues are 0, 3, and 3 again. So 3 has algebraic multiplicity 2. So you can play exactly the same game as we did here on top. But now instead of A minus alpha V, you get A minus 3 alpha V. So now the only thing you want is that A minus 3 of alpha is smaller than 0. So now we find synchronization when A minus 3 alpha is smaller than 0, which of course translates to alpha has to be bigger than A over 3. So in other words, again, we find that synchronization is easier in the lower system than it is in the top system, in the sense that we need alpha always has to be big enough. We find a condition that alpha has to be bigger than a certain value. But in the lower case, we find that alpha only has to be bigger than A over 3, whereas in the top network, alpha had to be just bigger than A, right? So synchronization is easier in the lower network. And so why is that probably correct? As in, why is that consistent with our intuition? Because again, we see that the lower network is better connected than the higher network. Literally, if we take the top network and we add another condition, another edge, that's precisely how we got the lower network. So the lower network is better connected. And again, indeed, that means that synchronization is easier. Now, what did it mean in the mathematical world? Right? So how did we arrive at this conclusion? Well, we looked at the eigenvalues of both the Laplacians, and we saw that each of them has an eigenvalue 0. But then if we order the eigenvalues by size, right? So it's 0, 1, 3, and here it's 0, 3, 3. Then the first non-zero eigenvalue was this 1 over here and this 3 over here. So that was the one that mattered, right? So we found that this eigenvalue 1 was the one that we used in our analysis to see if we're going to synchronize or not. So that's the smallest non-zero eigenvalue. And here we saw that that value was much bigger. That value was 3. So that means that synchronization, we concluded, was easier. So that is the eigenvalue that matters. And that is the way in which that matrix, the Laplacian, plays a role. So having set that up, uh, we now believe that the Laplacian is the object to analyze. So let's give some quick fire facts about the Laplacian so that we can play this game for general linear networks. So let's clear the page. First of all, how do you get the Laplacian, right? So, well, we found one way, namely, um, we write the equations of motion for the coupled system. We write it as a linear system, and then we get the Laplacian out of that. Sure, that's a way to do it. But of course, you just want an easier recipe to see precisely how this L how this matrix corresponds to your network, right? So the way to do it is you first build the adjacency matrix of a network. So this is always going to be a matrix. Both the adjacency matrix and the Laplacian will be n by n if n is the number of nodes. So first you draw the adjacency matrix. So the adjacency matrix, at least for these kinds of undirected simple networks, are very easy. You put always zeros in the diagonal. So let's say that this is node number 1 and the others are 2, 3, and so forth, and so forth. So you put a 0 on the diagonal, and then whenever there is a connection to node j, then you put a 1 there. So there's a connection from node 1 to 2, so I put a 1 at position 1, comma 2. There's also a connection here from 1 to 3, and there's also a connection from 1 to 4 in this example. So it's going to be a symmetric matrix, A as well, so I may as well put 1s here. I know there are zeros on the diagonal, and so now I look at node number 2. Number 2 only talks to 1. I already have that over here, so the rest are zeros. So in fact, for this network, these are all zeros, the remaining entries. So this is an example of a star network, which you can probably see why it's called that way. And what you can, for instance, check when building the adjacency matrix is that the number of ones that you have here, so the number of entries that is not 0, right? It's only 0 or 1, is precisely equal to the number of connections times 2. So then how do you build the Laplacian? Well, the Laplacian is then just going to be the degree matrix, and I'll tell you a bit about that, minus this adjacency matrix. So what does that mean in practice? In practice, you copy the adjacency matrix, you just copy all the entries, and you put minuses in front of it, right? So this is the easy part. And then what you get to do is you get to put entries on the diagonal such that the complete row sum is 0. So here I see 3 ones with the minus. So I put the 3 there, which is of course exactly the degree of node 1. So here on the column, on the row, I see only a -1. So I put a 1 here and then zeros for the rest, so that I know that it has row sum 0. So I just put the degree on the diagonal and the rest is 0. And this gets me that Laplacian. So you can check in the previous examples that this is precisely what we did. So some facts about the Laplacian. things that you will see or that you can check that you didn't make a mistake. So first is the Laplacian is a symmetric matrix, and that means that it has only real eigenvalues. As a matter of fact, we can find an orthogonal system of eigenvectors in which to diagonalize it. Now, another thing is that 0 is always an eigen value. So this is very easy. You can always check that because of the constant row sum, you can always plug in a vector like this with just the same entries, for instance, 1, 1, 1, 1, 1. You plug it in, you find 0. So 0 is always an eigenvalue. However, you might be wondering, are there networks where this eigenvalue 0 has a higher multiplicity? Turns out, yes, but only in a way that's fully understood, a way that you can easily understand. So, as it turns out, that the cardinality, the algebraic multiplicity of the eigenvalue 0 is precisely equal to the number of components. So what do I mean by the number of components? So this example matrix is, of course, completely connected in the sense that you can take any node and then you can walk to any other node, and then you can from that node walk to any other node and walk back. So this is a single connected network. So this has one component. Of course, I can also think of networks with two components, two connected components. Just add another network, maybe even an isolated node, and see that as the new network. So this can now be seen as a single network with three components. And that means that the eigenvalue 0 for the corresponding Laplacian appears precisely 3 times. Now, this is very easy to prove. You just note that you can block diagonalize the corresponding Laplacian corresponding to all of these components. There is a proof in the lecture notes that the eigenvalue 0 does not appear even more. So you just have to show that the uh, algebraic multiplicity of the eigenvalue 0 is precisely 1 for one of these connected components. And there's a very easy, very elegant argument in the notes that I sent you. So another thing that you can show, which is, again, it's not hard to see this, is that all of the eigenvalues are non-negative. So in other words, um, the remaining eigenvalues are always positive. So in that sense, you can always order the eigenvalues as such. So lambda 1, right? If you order them by size, then lambda 1 will always be 0. Lambda 2 will be bigger or equal to lambda 1 and will only be equal to lambda 1 once you have more components. And in that way, you can start ordering the eigenvalues of the Laplacian. And the total of them will be n, which is the total number of nodes. And so this is what we have been using all the time, right? So this eigenvalue was the important one because this eigenvalue determined how fast you can get synchronization. And of course, if this one is 0, if this one is 0, then there will be no synchronization. And that makes sense because then you have two disconnected components that are not talking to each other. So then, of course, from a physical point of view, synchronization should be utterly impossible. And so, since we can always write these linear systems as x dot is A times identity, which corresponded to the isolated dynamics minus alpha times the Laplacian. Since we can always write these systems as such, we see that this system can be stabilized, so the synchrony subspace can be stabilized by a condition that is precisely going to be simply by diagonalizing alpha that A minus this lambda 2 times alpha has to be smaller than 0. So we precisely, in the general case, get the condition that alpha, this coupling strength, has to be bigger than A divided by this lambda 2, this Fiedler value. This lambda 2 is called that Fiedler value. So what we see is that synchronization is possible um, precisely when alpha is bigger than a certain bound, and that certain bound goes down. In other words, it becomes easier to synchronize when this lambda 2, this Fiedler value, goes up, which you can make precise corresponds to the connectivity of of the network, right? So it has an interpretation of the connectivity of the network. So this is all according to our intuition. And of course, you can play this game in much bigger generality. So suppose now that our eigenvalues, sorry, that um, our network has nodes that have internal phase spaces that are not R1, but maybe R2 or R3 or R a million. So now suppose that the nodes themselves are quite complicated. You can still write an ODE, and then you can still write an ODE that corresponds to a network system, and then you can still analyze that using the same sort of techniques. So suppose I have xi dots, and now xi is the node of is the state of a node, but it's in Rn or Rk, something higher dimensional. But suppose it's still linear. So suppose I have xi dot as bxi, and suppose that it talks to some other nodes. So I'm going to have a coupling strength J, a coupling strength alpha, and I'll have a summation over all the nodes. Here I get my adjacency matrix, which recall is 1 or 0. Then I can still create some big ODE on the phase space Rn times k that generalizes this construction. So as a matter of fact, I can make it a little bit more complicated. I can say that it doesn't depend on xj minus xi, but some linear function h of xi minus xj. So now again, the state of the individual nodes is not 1D anymore, but maybe higher, right? So h is some linear map from Rk to Rk. So now I have some more general coupled cell network system. And so what it turns out that you can do is you can write this, I can stack all of these variables together to get some kind of a big variable x. So x is just the state of all the nodes stacked on top of each other. So that's n copies of Rk. So this is going to have m times k entries if you want. And then it turns out that I can very succinctly write this ODE as x dot is identity tensor, and the precise definition of this tensor product is explained in the lecture notes, times b times that x, and then I will get minus alpha times the Laplacian tensor H. So this is the full system. And then you can again analyze this by noticing that you can diagonalize the matrix L. And if you then work a bit, you get a new system or a bunch of new uncoupled systems, the same as the number of nodes, but of course now there's no interpretation of that they precisely correspond to nodes anymore, but you get n systems that are completely uncoupled, and they will look like this. So now they're indexed not by the nodes, but by the eigenvalues of the Laplacian. And I should put an H here if I do it that way. So here I put my new variable u. So now you can pry out n systems, one corresponding to each eigenvalue of the Laplacian. So that's that lambda I. And you get the following system. Now, of course, at least one of the eigenvalues, and precisely one of the eigenvalues, lambda I will be 0, and then you just get ui dot is b times ui, so that corresponds to the fully synchronous space, where as before we just get the dynamics of the original system. And if you but if your lambda is non-equal to 0, then it will have, you can see it as the dynamics of the individual nodes plus some kind of a correction term that has to do with alpha and your eigenvalue. So again, heuristically, of course, if H is a general matrix, all kinds of weird things can happen. But heuristically, when you turn on alpha, you make it go from 0 to non-zero and you make it increase. Then the first time that this hits some kind of a critical value will, of course, be well, the important values are of course the extremes. So the lowest value of lambda I and the largest value of lambda I. So you get precisely the same kind of system. In particular, if H is the identity and you wanted to synchronize, you need to subtract a constant times identity from B. And if you want to do that such that all the eigenvalues are negative, then that is hardest for lambda 2, that smallest value of lambda. So you again get that the Fiedler eigenvalue is important. But of course, there are many other things that you can start doing with that. So that is going to be the end of this lecture. So the next lecture, we will only look at nonlinear systems. And but that's going to be the next one. So this finishes the story about the linear ones.